Good afternoon. I just want to welcome you to another Biostatistics lecture series. I do have evaluation forms. If you don't have one, please raise your hand. And on the back, you'll find that there's the disclosure on the back. There's also a handout, so if you didn't get that, please raise your hand and I'll come around. And our speaker today is Dr. John Klein.
Okay, thank you, Kelly. What I'm going to talk about today are a whole body of statistical methods that are quite useful in doing medical research, and these are what's called non-parametric statistics. And I'm not going to go into a lot of details in terms of formulas. I'll show you one simple example of using non-parametric statistics, and then try to give you some idea of why you may want to use these. So I'm going to start out by just trying to define what a non-parametric test is, and then show you a simple motivating example of looking at some paired data where you get some very simple answers using non-parametric tests, and then try to give you some idea of why one would want to use non-parametric tests, a little bit about why maybe you don't want to use non-parametric tests, and then I'm going to give you a whole lot of names and show you a number of different kinds of things you'd want to test and try to tell you what non-parametric statistic goes with it, but I'm not going to spend any time on formulas and things like that. You can look these up, or if you're going to apply them, many of these procedures come out in a lot of the statistical packages. So, what is non-parametric statistics? Well, first of all, we need to have some idea of what parametric statistics are. There's a non-parametric, there should be a parametric statistic. And parametric statistics are usually what you see in an elementary statistics class. They're a whole body of methods that assume some underlying model for the data. And usually what you see in an elementary course is a normal distribution or a bell-shaped curve for the underlying distribution. And you want to make inference about some quantity that summarizes the population. Those quantities are called parameters. So with the t-test, for example, you may want to make inference about a mean, assuming that you have a bell-shaped distribution, or you may want to make inference about a variance, or you want to compare means, but always in the background there are some basic assumptions about what the underlying distribution looks like. If the model that you pick and the procedure you pick for that underlying distribution is correct, then everything's fine, and you do quite well in terms of making inference. But if you pick the wrong model, well, you could be misled. So here are just a few examples of some classic parametric procedures. The usual t-test, at least when the sample sizes are small, assumes that you have a bell-shaped curve. Analysis of variance, if you're used to that, which is a way of comparing two or more groups, assumes that you have an underlying normal distribution for each one of the different groups. Things like logistic regression assume you have a binomial distribution. If you look at correlation coefficients, the usual Pearson correlation coefficient, and I'll say more about this towards the end of the talk, assumes you have a bivariate normal distribution. So again, you have these bell-shaped curves that are floating around. And particularly when you have small sample sizes, you can be misled if these assumptions are not correct. So non-parametric statistics, as I said, is a whole body of alternative statistics that are available. They're sometimes called distribution-free statistics, if you go to the literature, because we don't assume any underlying distribution for the data. They're good for populations other than normal distributions. In fact, they're good whatever the underlying distribution is, and you don't have to make any assumptions about them. They're typically based, instead of on the data, on the ranks. A rank is simply the smallest value is given a rank of 1, the next smallest a rank of 2, and so on. So we kind of usually tend to throw away the actual numbers and just use the positions that we have, the rank of the observation. or they're based on simple counts, as we'll see in the example I'm going to show you in a minute. They have the advantage that you don't, because they're based on ranks or counts, you don't have to have good, exact data. You can do these when you have ordinal data, when you simply know that A is bigger than B is bigger than C. You don't have to know that A was 1, B was 2.7, and C was 11.5. Because we don't use that information, we simply use the ranks. Okay. Now, let me show you a simple example of two non-parametric statistics, perhaps the simplest two. And this is a simple study that I took from the literature looking at the effects of a tranquilizer on the Hamilton Depression Score, which is a score that measures how depressed people are on a, I think it's a 5-point scale. The lower the number, the less depressed you are. Okay, it's a series of questions. Some of you may be familiar with it. And the experiment was to measure this depression score in people and then give them a tranquilizer prescription for a period of several weeks. Then have them come in and, again, measure the depression score at a second visit. And what was hoped was that people on tranquilizers would be less depressed, so they would have lower Hamilton scores at their return visit than they had at their initial visit. So since that's what we want to prove, we make that the alternative hypothesis. And the null hypothesis is that there's no change in the depression score. So here's the data. This may not have shown up on your handout, but you can see here that the scores initially range from 3.16 up to down to a half. This is on a 0 to 5 scale. And then we have the post score. And because we have two scores on each individual, a pre and a post, what's done, whether we're going to do a parametric test or a non-parametric test, is we throw away the original data and we only work with the differences. So here's the difference between the pre and the post, the change in score. And a positive difference because of the way I subtracted them meant that they're less depressed. And a negative means that they're slightly more depressed after being on these tranquilizers. Now, one thing to note is that some of these numbers are fairly big. Some of them are pretty small. It may not be true that the data is actually normally distributed if we were going to do a paired t-test here. But we don't have to worry about it. We're just going to look at it as a non-parametric test anyway. So I'll show you two simple non-parametric tests to show you that they can be done very easily. And the first is the sign test. So what I've done is I've simply repeated the data here, the differences. And the one in red was the only negative difference, the only one where the person actually got worse. So as I said, the non-parametric tests involve either simple counts or ranks. The sign test is very simple. Just count up the number of positive differences in the sample. And here we have 8 out of 9. Now, under the null hypothesis, a patient should be equally likely to go up or go down if the tranquilizers don't have any effect. So this number here should be like the number of heads we would get if we flipped a fair coin 9 times, if there was really no difference in the pre and post depression score. So we can compute then from this simple number very simple values, just the probability of seeing as many positive differences as we saw or more, if we're looking at a one-sided alternative hypothesis, or twice that value if we have a two-sided alternative hypothesis. From this data, we can look in that in a table, and we can find that this number turns out to be 0.019. So that's the p-value. So we get several things here. We have a very simple test. You can almost do this test in your head. You don't have to have a calculator to compute the mean and the standard deviation. We get here exact p-values, which we don't necessarily get for some of these other tests, but we can get this number exactly, or there's a large sample approximation we could use. And we very easily get out our answer here, in this case, that there is some evidence that the Hamilton score is decreased by using the tranquilizer. Yes?
Why did you have the bad luck to have one had a 0 in there?
What you do with the sign test is you count the number of positive differences out of those where you can tell whether it was positive or negative. So you just reduce your n by 1. Yeah. All these methods have corrections for things like that, and corrections, as we'll see, for ties when you start doing ranks. You put in a mid-rank and so on. So that's a good question. All right, so that's a simple test, the sign test. It's when I do consulting and I have data like this is the one I just do this in my head. I think most of us could do that. Second test that you could do here illustrates the use of ranks. And this is a test that's called the Wilcoxon sign rank test. And the idea here is that we have the differences again, and we ignore the sign of the differences. So we just take the raw number, forgetting about whether it's positive or negative, and rank them from smallest to largest. And the smallest without a sign gets a rank of 1. So this is the smallest number. The next smallest gets a value of 2. The next smallest, which is this one without the minus sign, gets a rank of 3, and so on. Okay? So, as I said, most non-parametric tests involve using some type of ranking scheme. Here, what we do for the sign rank test is we just add up the ranks associated with the positive numbers. Now, if this number is too big, that means that we have almost all positive differences, or that all the positive numbers tended to be the biggest ones. So that's good evidence that there really is something going on, that there's a difference here. If this number is way too small, that means either we saw very few negative differences, and again, we should see about half of them, or the negative differences were all tiny numbers and the positive differences were all big numbers, and that also says that something's going on. So what we do here is we compare the sum of the positive ranks. We could equally have well done the sum of the negative ranks to the average rank that we would see if there was no difference. And these numbers just come from doing some simple combinatorics. So the average rank is n times n plus 1 over 4. And then we can either find a p-value by looking at a table. And I'll give you a reference at the end here of a book that has tables for all these statistics that you can just look these numbers up in. Those tables are created by basically looking at all different arrangements of these ranks where they could be, one could be positive and one could be negative. So it looks at, in this case, literally hundreds of these and then counts how many of them are more extreme than others. Or we can use a large sample approximation, which I've written at the bottom of the slide here, and use the fact this is approximately normal. So again, we don't use the original data, but we use these ranks. We use their position. Now, think here, if you have an outlier, the outlier is not going to contribute as much here. Over and above, if to the ranks, it may well be the biggest of the ranks, fine, but it's not going to really tip the scales here having one or two outliers in doing this. So in our example here, the ranks have to add up to be 45. I'm just plugging some numbers in these formulas. We saw a positive, we added the positive ranks together, we get 42, or, well, there was only one negative rank, which was 3, so I can get it by subtraction. I could just go to a table in a book, and it tells me the p-value is 0.006. So again, there's evidence that the Hamilton score is being decreased. Or I can use a normal approximation by plugging things into the formula that I have here. So again, this is fairly easy to do. You could do most of these on a calculator. And of course, there are packages, computer packages. Most of them will do these automatically for you. Okay. So this is the only math I'm going to show you in the talk if you're at all worried here. So let me try to explain why you would want to use non-parametric statistics. And the first reason you want to do this is because there are much fewer assumptions that you have to make than if you're using parametric statistics. Nowhere did we have to assume we had a bell-shaped curve here, or do we have to assume that we have a particular form for the underlying distribution. There really were no assumptions that we had to make. There may be some assumptions about symmetry in some cases, and that's probably the most stringent assumption that we have to make. A second reason to use non-parametric statistics, when the sample size is small, we get out exact p-values. We can get these from a table. Most computer programs will give them directly to you. Some of them will give you exact p-values by simulation and then enumerating all the possible samples and seeing how extreme is your sample compared to everything else. So that's a nice feature that we don't necessarily have when we have non-normal data and we start applying some of the normal procedures. As you can see, at least I think they're easier to apply. They involve just ranking things that you can do on a spreadsheet or whatever, or simple counts. They don't involve a lot of sometimes strange calculations. I also think that another reason to use them is they're easier to understand why they work. This may be debatable. At least to me, they're easier to understand why the sign test works than perhaps why the t-test works when you have the ratio of some sum over some sum of squares. Why is that really a reasonable thing? A major advantage of non-parametric statistics is that they do not require numerical data, but they can be performed on ordinal data. So if you think back to both of the examples, we didn't need the raw numbers. All we needed was the ordering of the values, or we simply needed to count whether they were positive or negative. The actual value was immaterial to us. And as such, because of that, they're quite useful when you're looking at scales and you're looking at questions that you may do on a survey where you have 6 different ordinal categories, and you want to compare these between individuals. It's hard to do a t-test when the numbers are 1, 2, 3, 4, 5, but you can put them in some kind of an order. Although there may be a lot of ties, so you gotta deal with that somehow. Another reason I really like non-parametric statistics is that they can be used for very complicated hypotheses. More complicated hypotheses than you can do with classical statistics. And a good example of this is the problem of comparing k-groups. So we want to test the null hypothesis that the groups all have the same mean or central tendency versus the hypothesis that at least one is different. And if we use a parametric test, we can do this. This is a fairly easy and standard problem. And we can use analysis of variance, or ANOVA, if you've heard about that. There's a corresponding non-parametric test called the Kruskal-Wallis test that will also do this. So it doesn't really save us much there. But on the other hand, if our alternative hypothesis is that the means are ordered in some way, that population 1 has a smaller response than population 2, than population 3, You could think of these as being different doses of drugs, and you want to, as you get a higher dose, maybe you get a response that gets to be higher. There's really no good way of testing this with normal theory data. There is a way, it's called isotonic regression, and sometimes you see it in a PhD program, but not always. On the other hand, with non-parametric statistics, there's a simple test called Jonckier's test. And Jonckier's test allows you to test the hypothesis that the means are ordered versus whether they're all equal, or whether the medians are ordered, whether the groups are ordered in some way. So that's a really, for me, a big plus of non-parametric statistics, is you can do these sort of weird things. And I'll show you a couple other tests a little bit later. Now, you can also get exact confidence intervals as well as getting exact tests using non-parametric statistics. So you can get a confidence interval that has an exact coverage probability, particularly for small samples that may not be valid if you use a parametric test. And these confidence intervals are usually based on the ranks of averages of 2 points. So there's something called Walsh averages. Another big advantage of non-parametric statistics is it gives you some protection against outliers. If you have some weird data, one or two observations that are outliers, because we're looking at ranks, they don't have as much of an influence as they may have in a parametric model. I think you'll find in most software packages, SAS, R, Stata, SPSS, you will find some non-parametric statistics available for you to use. And certainly the simplest ones are there. For those of you that are a little more advanced in statistics, if you really can't find it, quite often you can get the non-parametric tests by replacing the data by ranks and then running the parametric test. And that will automatically give you the right test. So, for example, if you wanted to get the Crisco-Wallace test statistic, just replace the data by ranks and run a one-way analysis of variance, and it'll give you the same numbers. Not necessarily the right p-value, but it'll give you the statistic out. I think I just said this. Did I go? I must have gone the wrong way here. All right, why not use non-parametrics if they're such great things? Why not just use them all the time? Well, the problem is that if you pick the right parametric model, you can do better. You have a higher power for your test. That means that you're more likely to reject, the not should be here, that's the typo. More likely to reject the null hypothesis when it's false. Okay? So you have a better chance of making the correct decision when there really is a difference. The loss of power that you have depends upon how poorly you made the assumption for the parametric test. Okay? And in most cases, it depends, as I'll show you in a minute, on what the tails of the distribution look like if you did a histogram for the entire population, how thick they are compared to, for example, a normal distribution. And it's usually measured by something called the asymptotic relative efficiency of two tests. And what this is the sample size that you would need for the second test divided by the sample size for the first test to achieve equal power for the two tests. So if the tests are equally good, the asymptotic relative efficiency would be 1. Okay? The same sample size for both tests would give you the same power, and then you can pick either one. If this number is less than 1, then the second test is more powerful. And if you want to get the same chance of making a correct decision, then the sample size you need for the second test is some number less than 1 multiplied by this number n1. So for example, if the asymptotic relative efficiency was 0.5, then you would need twice as many a sample size of twice as big for the first test than you would for the second test to have equal power. Now, how much do you lose? Well, it depends a bit on the test, and this figure may be a little complicated. What I've drawn here are curves that match up with the different colors, and it depends on what the underlying population distribution looks like. So you can think of this as being a histogram if you could measure everybody in the population. The blue curve here is the normal curve. And I'm comparing here either the sign test or the sign rank test to the normal curve. Okay? A number that's smaller than 1 says the normal does better. The t-test does better. A number bigger than 1 says that the t-test does worse. So if we just look at the uniform distribution, which is this flat curve, you can see that if we have data from the sign test, the asymptotic relative efficiency is the third. So if you needed 100 observations with the t-test to get a particular power, you would need 300 observations if you're going to use the sign test to have the same power. On the other hand, if the data really came from this purple curve, the double exponential, the value is 2. So you're better off using the non-parametric test than the t-test. Okay? And this says that if you want the same power, if you had 100 observations and you got the power you wanted with the t-test, you'd only need 50 observations with the sign test. And the value here ranges from, the sign test, of course, remember the sign test just simply used yes or no, was it a positive or negative. You can lose quite a bit. If you use the sign rank test, the second one, you can see if the data was really normal, the asymptotic relative efficiency is 0.955. So you don't lose much doing a sign rank test, but you gain a lot for these other distributions. But it is something to keep in conscious of, that we can lose some power by using non-parametric tests. Okay, a second reason not to use non-parametrics, a big reason is to use them when they have small sample sizes, because we can be somewhat misled. If we have large sample sizes, well, the central limit theorem, which says that the mean has an approximate normal distribution for large samples, sort of the basis of statistics, says that if we have a large sample size, then these t-tests, analysis of variance, all these ones that assume normal distributions are going to work for us because of the central limit theorem. So in a way, all these normal theory tests are also non-parametric tests for large samples. So I really think non-parametrics is best for small samples, and for large samples, we're probably okay using the central limit theorem. Okay, so let me give you a list of some of the tests that are available, non-parametric tests, for various situations, and just sort of go through a catalog of these and give you a little bit about how they work. Now, we've already talked about one sample and paired sample tests, and we've looked at the paired t-test as a parametric test. The sign test and the Wilcoxon test, sign rank test, are the best tests for the underlying distribution for this problem. And you can also find confidence intervals. Sometimes in books you'll see that these are confidence intervals based on what's called the Hodges-Lehmann estimator, and that's the statistic that's used to find confidence intervals here. So not much to say about these. If we have two independent tests, two independent samples, and we want to compare location, well, we already have a slight problem with parametric tests. We have the usual t-test that you probably saw in an elementary stat course or earlier in this lecture series. And that t-test assumes equal variances between the two populations. And if that's not appropriate, then the test may not work well. There is another t-test that's used sometimes. It's called scatter weights approximation that allows for different variances in the two groups. For non-parametric tests, we don't have to make that assumption. And there is a test that can be used called it's called by a number of different names. It's called either the Mann-Whitney test, it's called the Wilcoxon test, or it's called the Mann-Whitney-Wilcoxon test. There were two papers that came out in 1948 independently by two different people that have two different formulations of the test. And for a while it depended where you went to school, but now everybody usually says Mann-Whitney-Wilcoxon test. And they're simple tests. What you do for at least the Wilcoxon version is you just pool all the data together, forget which sample it came from, rank the data, give it a number, 1 to the smallest and so on, and you just add up the ranks of the first population in the combined ranks. And that should be sort of a mid-range number, a number kind of in the middle. And then there are tables of these things. There are other non-parametric tests here that are sometimes used. They're called linear rank tests. And again, I don't want to go into too much detail, but the idea is you have the rank of the ith observation in sample 1 in the pooled sample, and then you add those ranks up, similar to what you have in the Mann-Whitney-Wilcoxon test, except now you have some weight that you use. And that weight allows you to give more power to different kinds of hypotheses. Those of you that have done survival analysis and you've heard of the log rank test, that's a special weight, case of this weight when you have censored data. But usually what we do here is the Mann-Whitney-Wilcoxon test. There are two sample tests for comparing two variances, if that's what you're interested in. The parametric test, again, it assumes normality, is an F-test, where you look at the ratio of the two sample variances. The non-parametric test here is what's called the Ansary-Bradley test. And the idea here is that, again, you rank the data from smallest to largest in the pooled sample, and you assign a score. And the smallest and the biggest get a score of 1. The next smallest get a score of 2. The second one's in. The third one's in, get a score of 3. And you keep going until you get to the middle. And then you add up the scores for the first sample. Now, if the middle is the same for both, if they're equally variable, then the first sample should have sort of a mix of these values. If one has a smaller variance, you would expect that most of its values are going to be towards the middle, and it's going to get bigger numbers. And if the population that you're adding up is more diverse, it's going to tend to have more smaller numbers. So that's sort of the idea here of this guy. And there are tables that are constructed that you can use, and it's in some computer packages. It requires that you assume equal medians. If they're not equal, then you can use what's called Miller's jackknife test. Okay, now, non-parametric tests also allow you to do what we call omnibus tests, where instead of comparing location or comparing spread, we simply want to know are these two populations that we sampled from the same or not? They could be different in location, they could be different in spread, they could be different in God knows what parameter. So there are no real corresponding parametric tests. The non-parametric tests that you might see are usually based on what's called the empirical distribution function, where you look at a particular value, x, and you count how many observations were smaller than that, and you divide by n. Okay, and if you do that and you compare those for the two different groups, the F and the G here, and you take the maximum of the difference, then this is not a vodka. This is really a statistician. You get the Kolmogorov-Smirnov test. Were it a vodka, it would be much better this afternoon than probably listening to this. So that's a common test that gives you a global comparison of the two curves, the two populations. There's another test called the Kramer-von Mises test, and instead of looking at the biggest difference between these two curves over x, it looks at the area between them. So these are some, are omnibus tests that you don't really get with parametric methods. All right. As I said, the one-way layout, here we have three or more independent groups, and we want to compare these three groups, usually the location or the mean or the median of these three groups. So the parametric test assumes we have normality and usually assumes we have equal variances, and this is called analysis of variance. Now, for non-parametric tests, we have a number of tests depending upon what the alternative is. For parametric tests, we can only test, as I said before, the alternative that these taus, and you can think of the taus here as being the median in the jth group. Okay? So we can only test whether the medians in all the groups are equal versus whether they're not. And that's what the analysis of variance does. And that's what the Crisco-Wallace test does. If, on the other hand, we wanted to test the alternative hypothesis that the medians are ordered in some way, then we can't do that using analysis of variance, using normal theory, but we can do it using the Jonquière-Terpstra tests. Okay? And what this does is it kind of looks at all the Wilcoxon two-way tests comparing groups and make sure that they're ordered in the right way. We can even do something a little bit weirder. We can do what's called umbrella alternatives. And here the idea is, if you're giving a drug, well, maybe the median gets to be bigger as you give doses, but then at some point there's a threshold, and then it starts to get smaller afterwards. So the alternative is the median between groups looks like an umbrella. Okay? Again, I don't know of any way you can do this using parametric statistics, but there is a test called the Mack-Wolf test that allows you to do these things. So this is a big plus of using a non-parametric statistics in my mind. Okay, we can also do non-parametric tests for the what's called the two-way layout. Here we have subjects. We have n subjects, and each subject is given one of k treatments, where k is at least 3. It's like having paired data, except now we have 3 treatments instead of 2 treatments. And we can have multiple replicates on the same person. And for a parametric test, there is a version of analysis of variance that will let us do that. For non-parametric statistics, there's a test called Friedman's test. The tests the alternative that the taus are not equal, and the test works by doing rankings within blocks and then adding up these rankings within blocks in an appropriate way to get an overall test. Not using, taking into account the block effect leads to some differences in, sometimes leads to getting the wrong conclusion here. Okay. Yeah, the final, again, non-parametric statistics can be used for a lot of things. Measures of association, and this is one thing that I think is often confused. People are used to using what's called the product moment correlation, where you take this is sort of what you learned in an elementary statistics course. It gives you a number between -1 and 1. It's the value that you get, the r squared, that comes out of fitting a straight line. And it's a measure of the strength of linear association. But it turns out that it's only a good measure when the data is bivariate normal. If the marginal distributions are not bivariate normal, and you use this, the number is almost meaningless. You can have, with normal data, you can get, if you have a value of, say, -1, that means that all the points lie on a line. If you have non-normal data and you get sometimes you can't even get -1. Points can lie on a line, but the smallest number you can get is like -0.4. So the numbers don't necessarily make sense. I personally never use it because of that. But there are two non-parametric tests. And they're usually available in most computer packages. The first test is Spearman's row. And what Spearman's row does is it takes and replaces the original observations by ranks and then computes the usual correlation coefficient. And this gives you a number always between 1 and -1, irregardless of what the underlying distribution is. It gives you 0 when you have independence. And when you have a linear relationship, it gives you ± 1. A simpler, sometimes, measure is what's called Kendall's tau. And Kendall's tau works fairly easily. We say two pairs are concordant. I have the formula here, but the basic idea is that two pairs are concordant when, for one pair, the x is bigger than y, and the other pair, the x is also bigger than y. They're discordant if in one pair the x is bigger than y, and in the other pair the y is bigger than x. So those are discordant pairs. Doesn't matter how big or how small they are, it's just looking at the ordering of the x's and the y's. And what Kendall's tau does is it computes, adds up the number of concordant pairs, subtracts off the number of discordant pairs, divides by the number of comparisons you make, and that gives you Kendall's tau. If you have perfect positive association that when x gets bigger, y also gets bigger, then Kendall's tau is going to be +1. If you have perfect negative association, when x gets bigger, y gets smaller, you have a tau of -1. Okay, so a few remarks here, and then close. As I said, most of the methods are available in most software packages. If you really had to buy a package just to do non-parametric statistics, Minitab is the best one. The reason I think it's the best one is it has all the non-parametric confidence intervals in it. If you want a good reference that's relatively easy to read and has every table in the world and every non-parametric method in the world, there's a book by Hollander and Wolf called Non-Parametric Statistical Methods that's a very good reference book. Has a lot of examples. It has the theory kind of in footnotes, so you don't need to know it, but you can look at the examples. you're a baseball fan, he's got some nice baseball examples in there about running bases and things like that. Okay. Summarize, I think non-parametric statistics provide a viable alternative to traditional normal theory statistics. I would use them, and do use them, when the sample size is small, when I want protection from outliers. Certainly use them when I have ordinal data. I think they're useful when you're modeling association between variables. They're also very useful when you have ordered or umbrella alternatives. They're certainly what you want to do if you have survival data or something that looks like survival data. And most of these non-parametric statistics have versions of them that account for censored data. So, let me stop there. If you have some questions, certainly take those. Just a reminder that we're available for help. And if you have questions and you want to apply some non-parametric statistics, we have our drop-in service, so you can certainly come and get help or come over to the Biostatistics department. Okay. Any questions, comments? Yeah.
Is there a way to check for underlying distribution of the data and decide whether you want to go with parametric or non-parametric?
Yeah, there's a whole body of tests that are available for testing for normality. The best way, if you have enough data, is to make a plot. Most packages will have something called a Q plot, where you can plot the data in a certain way, and if it looks like it's a straight line, that tells you that normality is reasonable. Or you can make a histogram of the data and see if it looks like a bell-shaped curve. Or, as I said, there are tests for normality. There's a test called the Anderson-Darling test. Depends what package you're using. I mean, some of the packages will just allow you to test for normality. I know in SAS you can just say in proc univariate that you want the normality test. Of course, the problem is if you have relatively few observations, those tests are not very good because, you do a histogram with 8, cases. It's kind of beyond me to look at it and say whether it looks like it's normal. I can kind of look and see, is there some outlier? But certainly for small sample sizes, you usually don't lose much. And one way to do this, what I would recommend is, if the non-parametric tests are available in your package, is to run both the non-parametric test and the parametric test and see if they agree. And if they give you the same answer, then you're fine. If they don't, then come and see a statistician. That's quite often what I do if I really have to decide between them. If they give me the same answer, does it really matter? But no, there are ways. There are graphical ways. There are tests. There are tests. You can test for normality as long as you have at least 3 observations, because you have to estimate a mean and you have to estimate a variance. So, but it's not a very good test. I only know that because I had a roommate when I was in graduate school that did his thesis on that, and it wasn't very good, but it got him a degree. So, yeah, go ahead. I'm sorry.
Why don't people do that all the time? They have some kind of a standard of apply this test of normality, and if the result is more than this, use a parametric, otherwise use a non-parametric, rather than relying on all these kind of feelings.
Well, I think the reason is that you, in most cases, you're in this situation here where you don't lose much by doing non-parametrics. I mean, if you're using a sign rank test, the relative efficiency here is pretty close to 1. You're not losing much by doing non-parametrics, so that's why most of us that analyze data sort of routinely use non-parametrics when we have small to moderate sample sizes, because we know that we're not going to lose much. It depends, of course, on the test, but even with like the Mann-Whitney-Wilcoxon test, the asymptotic relative efficiency is not that small. It's really only the sign test that didn't use much information here that may be a little bit questionable. But that's kind of a quick and dirty test that I probably wouldn't put into a publication. But if you came to me for consulting and you said, well, here's my data, it's a kind of quick thing I could do to say, well, it looks like there's not much going on here. But I wouldn't, that's not what I put in the final paper. I would do something the sign rank test or something like that. So, you could do the test, but it's usually, the power of that test is usually pretty small. So, do you have a?
No, I was just asking that. So if you are suggesting that if there are some outliers in the data, then just go for the non-parametric.
Yeah, the non-parametric tests are not as affected as much by outliers as the parametric tests. Now, of course, if you really know that there are outliers, you'd want to fix those, but it is protection against having outliers. So, yeah, I mean, that's another reason to use it. Certainly, that and having ordinal rather than numeric data. Those are the two biggest reasons to use it. I know in the IBM-TR we use it all our univariate analysis we do using non-parametric statistics. We don't do t-tests or things like that. We just automatically do it. And you can do it using, as I said, most computer packages. Any other questions? Okay, thank you.